Hello students, welcome back. The final topic for lesson 5 is the proof of theorem 3.3. The proof of the theorem associated to even and odd permutations. Please recall that in 3.2 we established the decomposition by transpositions. Every non-trivial permutation is a product of transpositions. Remember that? But there's a problem. This product of transpositions is not unique. Also, the number of transpositions required is not unique either. What we can prove, however, is that the number is unique modulo 2. In other words, the number of transpositions required is either even or odd, no both. In short, if you have two different decompositions requiring odd transpositions or S transpositions, then R is even if and only if S is even, and vice versa, and R is odd if and only if S is odd, and vice versa. So you cannot have even decomposition in one hand and odd decompositions on the other hand. That's not possible, and that's what we have to prove. We're going to use the proof of contradiction here, like this. Suppose that we have even number of transpositions here and an odd number of transpositions there for the same permutation. And then what we're going to do is reduce two at a time, and eventually you're going to draw a contradiction in the end. That's what you're up to. 0 is congruent to 1 modulo 2. That's not right, of course. There goes the contradiction. But then again, how do you establish all that? Well, step 1 is the hardest, and that's where we're going to begin. Ready? Okay, here we go. Let sigma be a permutation and let tau be a transposition coming from the same symmetric group so that their composition tau sigma is well defined. And then the number of orbits of sigma and the number of orbits of tau sigma differ by 1. That's the hardest part. Remember, the number of orbits come from equivalence classes, you see. Given permutation, we get an equivalence class, and then we get equivalence partition. So the number of orbits is unique. Number of transpositions required, those may not be unique, but number of orbits, that's well defined, and those are unique. And then that of sigma and then that of tau sigma differ by 1. Either one more or one less. Now, if you apply that twice, you're going to get congruence modulo 2, you see. Number of orbits for sigma and the number of orbits to tau 2, tau 1 sigma. That means sigma first and then tau 1 and then tau 2. These two differ by either +1 or +1 or -1 plus 1, or finally -1 1. In any case, congruent modulo 2. Applying the first claim twice, right? They differ by 1, and then we apply it twice. So if you multiply two transpositions, or if you remove two transpositions, we have congruence modulo 2, 2 at a time. But of course, you have to get this one first. How do you do that? Well, we have to consider these two cases. Let tau be AB, and if the orbit of A and that of orbit of B are disjoint on the sigma, in order to avoid confusion, let me specify sigma. They're disjoint under sigma. Composing transpositions tau to get tau sigma will reduce the number of orbits by 1. So number of orbits goes down by 1. And then, if A and B both belong to the same orbit, under sigma, of course, composing transposition tau to get tau sigma will increase the number of orbits by 1. So either go down by 1 or go up by 1, depending upon whether A and B are disjoint or they belong to the same orbit. By the way, recall that we are talking about orbits which are equivalent classes, and equivalent classes are either identical or disjoint, nothing in between. So disjoint, case 1, identical, case 2. In case of disjoint, we have one orbit for A and another disjoint orbit for B. And A has length R, for instance, B has length S. Those numbers R and S are not that important, actually. And then the composition will join those two to get one big orbit. So two orbits reduce into one, and every other orbits are unaffected because tau will not affect anything other than A or B. So total number will be reduced by 1. So how do these two join together? Well, here we go. A goes to sigma of A, and then sigma of A go to sigma squared of A, and so on, all the way up to R minus first power. That's no different than just applying sigma only. Because after applying sigma I power to I plus first power, and tau will not affect anything other than A or B. So that's what this blue means. Tau does not affect at all. But in last case, R minus first power to A, and then apply tau, okay. Tau does affect because tau exchanges A and B, so instead of going back to A and then getting a disjoint orbit of itself, it leaps over to B. See this red? That's when this tau kicked in non-trivially. And then we do the same thing from B to sigma of B, and then the next, and then the next. Each time, just using sigma versus using tau sigma will make no difference, like this. J's power of B, and then J plus first power B, and that's it. But then again, at the last point, S minus first power, it goes to B, but then again, tau affects B non-trivially. It goes to A. So instead of ending here and coming back to just B, it goes all the way back to A, then we have one big cycle. One big orbit, excuse me. The result, in this case, number is reduced by 1. Two disjoint orbits reduced into 1, and everything else stays the same. Now let's consider the other case. Argument is the same, so let me go ahead a little bit more quickly. So this time, both A and B belong to the same orbit. So A all the way up to R minus first power, and then B, and then S minus first power all the way back to A, one big orbit. And then if we apply tau sigma instead, then we end up with breaking this apart. Same computation, A goes to sigma of A, and then sigma squared of A, and so on and so forth, all the way up to R minus first power. Whether tau is there or not is unaffected because tau kicks in only for A or B. But right here, instead of going to B, now tau kicks in, and instead of going to B and then joining to the next, we have cutoff and then going back to A, so only this one, and this one doesn't work. That red is cut off. Same thing here, B to sigma of B and sigma squared of B and so on and so forth. None of them are affected by tau, but at the very last moment, when it has to go to A, tau kicks in and sends it back to B only, so we have only this part. So red arrows are just cut off. So we have this, and then that one has two separate orbits. So number of orbits is increased by 1. You see, these big orbits were separated into 2, And then everything else, they're all unaffected because tau affects only A or B. So that's it. Either decrease by 1 or increase by 1. Consequent, the number of orbits of sigma and the number of orbits of tau sigma differ by 1. And if you apply that twice, and then if you multiply or if you compose two transpositions, you get either plus 1 plus 1, plus 1 minus 1, minus plus 1, or minus or minus 1. In any case, congruent modulo 2. So even versus odd will not be affected. So what are we going to do here? Let's suppose we have all these, and then using the second part, we're going to reduce the number of transpositions 2 at a time. Let's suppose that a permutation, a non-trivial permutation, can be decomposed by transpositions like this. Even number in one hand and odd number in the other hand. And then if we multiply two inverses to knock off 2 at a time, those inverses knock off 2 at a time, and then we're going to reduce all those transpositions 2 at a time. So go down 2 at a time, 2 at a time, and then the number of orbits of the original will not be affected, modulo 2. So we have congruence modulo 2, even if I just repeat it. So repeat it 2 at a time, 2 at a time, 2 at a time, go down, 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 and you're going to go down to, well, over here, nothing, go down to 0. So number of orbits of E, and then here, they are odd numbers, so all go down, and then we have 1 left. So number of orbits of mu E. So we are going to go down to that. And the left-hand side, of course, is the number of orbits of sigma. That's where we started. So that stays the same. But then again, number of orbits of E versus number of orbits of some transposition times E, well, they must differ by 1. Remember? Any permutation and then times tau times any transposition differ by 1. So we have to have either 0 is congruent to 1 or 1 is congruent to 0. Either way, they must differ by 1. There goes a contradiction. You see, the left-hand side and right-hand side must differ by 1. But on another angle, they have to be congruent modulo 2. There goes a contradiction. Either 0 is congruent to 1 or 1 is congruent to 0. Either way, modulo 2. That's not right. There goes our contradiction. In other words, 1 even when odd number of decomposition is impossible. So in any case, we need either even or odd number of transpositions, not both. So we can classify the permutations as even permutations, which require even number of transpositions, and odd permutations, which require odd number of permutations. And then even number of permutations, even permutations actually form a subgroup, which we call an alternating group. And this group will become important in abstract algebra 2 when we do some field theory, Galois theory. But for now, I'm not going to overemphasize alternating groups. It'll be too difficult. That completes lesson 5. Feel okay about the complexity of the proof? If you do, then great. You're doing good. If you don't feel too bad about it. Just remember the result.